Section: Introduction. In this section, we discuss the recent advancements in the reasoning abilities of large language models, LLMs, like OpenAI, DeepSeek, and Kimi, especially for complex math tasks. A significant method behind these improvements is reinforcement learning with verifiable reward, RLVR, which typically uses reinforcement learning with a rule-based reward system, such as a simple yes or no indicating if the model's answer to a math problem is correct. We have noticed interesting effects from RLVR, including the enhancement of certain cognitive behaviors, like self-reflection, and better generalization across various tasks. Currently, we are focusing on improving RL algorithms to boost RLVR's performance and stability. However, the data aspects of RLVR are not as thoroughly examined. While some studies have worked on creating high-quality math reasoning datasets, there is still much to learn about the role of data in RLVR. This raises important questions. How much data do we really need? What type of data works best? How do the quality and quantity of training data relate to observed behaviors like self-reflection and generalization? The most relevant research to these questions is LIMR, which introduced a metric called Learning Impact Measurement, LIM, to assess the effectiveness of training examples. They showed that they could maintain model performance while reducing the number of training examples significantly. However, they did not investigate how much we could reduce the RLVR training dataset. Motivated by these insights, we explore the question: how much can we reduce the training dataset for RLVR while still achieving similar performance to using the full dataset? Our findings reveal that we can reduce the training dataset to just one example. This supports the idea that base models already have strong reasoning capabilities and shows that a single example can greatly improve the model's math performance. We call this approach one-shot RLVR. We summarize our contributions and findings as follows. We found that using one specific example as the training dataset can yield performance similar to a larger subset that includes that example. For instance, this improved the Quen 2.5 Math 1.5b model's performance on a math benchmark from 36% to 73.6%, and from 17.6% to 35.7% on average across 6 benchmarks. Additionally, using 2 examples slightly outperformed the larger subset and matched the performance of a much larger training set. Interestingly, these examples were relatively easy for the base model to solve without training. Moreover, one-shot RLVR not only improved math performance but also enhanced performance on non-math reasoning tasks, even surpassing full-set RLVR. We confirmed the effectiveness of one-shot RLVR across various base models and different RL algorithms. We also observed a fascinating phenomenon called post-saturation generalization in one-shot RLVR, where the model's training accuracy quickly approaches 100%. Yet its test accuracy continues to improve. Even with just one training example, overfitting does not occur until after about 1,400 training steps. After overfitting, while the model's reasoning for the training example may become unclear, its test performance remains strong and interpretable. Additionally, we demonstrated several phenomena. One-shot RLVR works for nearly all math examples when each is used individually for training. 2. It allows for cross-domain generalization, where training on one example can improve performance in other areas. 3. As training progresses, both the response length for the training example and the use of self-reflective terms in downstream tasks increase. Through our studies, we found that the improvements in one-shot RLVR are mainly driven by policy gradient loss, distinguishing it from grokking, which relies heavily on regularization methods. We also highlighted the importance of encouraging diverse outputs, showing that adding an entropy loss can further enhance performance. Notably, using entropy loss alone, even without any outcome reward, led to a significant performance boost on a math benchmark. Similar improvements were seen in other models as well. We also discussed how this relates to label robustness. Section Summary. In this section, we explore the potential of reducing the training dataset for reinforcement learning with verifiable reward, RLVR, to just one example, demonstrating that this approach can significantly enhance the mathematical performance of large language models while maintaining comparable results to larger datasets. Our findings reveal that one-shot RLVR not only improves performance on mathematical tasks but also facilitates cross-domain generalization and highlights intriguing phenomena such as post-saturation generalization and the importance of diverse exploration in model outputs. Section: Preliminary. In this section, we adopt the GRPO algorithm as our reinforcement learning method for large language models, unless we specify otherwise. The GRPO loss function consists of three key parts: policy gradient loss, KL divergence loss, and entropy loss. We will briefly explain each part, with more details available in the appendix. First, the policy gradient loss motivates our model to generate response sequences that receive higher rewards. We assign weights to the outputs based on their advantages, reinforcing better solutions and penalizing poorer ones. Since we are focused on mathematical problems, we define the reward as binary, where a score of 1 is given only if the model's answer matches the correct one. Second, the KL divergence loss assesses how different the model's responses are from those of a reference model, acting as a regularization term to ensure good language quality. Third, the entropy loss, which we apply with a negative coefficient, encourages the model to explore more by promoting diverse reasoning paths. While this loss is not strictly necessary for GRPO training, we include it by default in our experiments, and we discuss its impact on one-shot RLVR later. For data selection, we introduce a straightforward method to rank training examples based on their historical variance score. We first train our model for a set number of epochs on the full dataset using RLVR. For each example, we gather a list of historical training accuracies, which reflects its average performance over the epochs. Recognizing that the variance of the reward signal is crucial for RL training, we rank the data according to the historical variance of training accuracy. Next, we define a ranking order where the examples are sorted by their variance scores. We select examples based on this ranking. For instance, the top-ranked example performs well in one-shot RLVR, and we also choose additional examples from various domains to evaluate under the same conditions, finding that some of these also perform strongly. However, we note that this ranking method is not necessarily the best for selecting individual examples, as many examples with moderate or low variance can still lead to significant improvements when used alone. We typically conduct our experiments using the Quen 2.5 Math 1.5b model, while also testing other models for one-shot RLVR. Due to resource constraints, we randomly select a subset of 1209 examples from the DeepScale R preview dataset for our data selection, which we refer to as DSR sub. After ranking these examples based on their historical variance scores, we maintain a consistent correspondence between the ranked examples throughout our experiments. To facilitate one-shot RLVR, we duplicate the selected data until we reach the desired training batch size and create a new dataset for our experiments. Section Summary. In this section, we adopt the GRPO reinforcement learning algorithm for large language models, utilizing a loss function that includes policy gradient loss, KL divergence loss, and entropy loss to enhance model performance on mathematical problems. We also propose a data selection method based on historical variance scores to effectively rank and select training examples, demonstrating that even examples with moderate variance can significantly improve performance in one-shot RLVR tasks. Section: Training. In this section, we outline our training process. We adhere to the Verl pipeline, using default values for the KL divergence and entropy loss coefficients, which are set to 0.001 and negative 0.001, respectively. The rollout temperature for training is 0.6, and we apply a weight decay coefficient of 0.01. Our training batch size and mini batch size are both 128, allowing us to sample 8 responses for each prompt, resulting in 8 gradient updates per rollout step. We set the learning rate to 1 millionth. The maximum prompt length is 1024 tokens, while the maximum response length is 3072 tokens for the Qwen 2.5 Math 1.5b, 7b model, which has a context length of 4096. For the DeepSeek R1 Distill Qwen 1.5b model, we increase the maximum response length to 8192 tokens, following the setup from stage 1 of DeepScale R. We save model checkpoints every 20 steps for evaluation and utilize 8A100 GPS for our experiments. The training steps for our models are 2000 for Qwen 2.5 Math 1.5b, 1000 for Qwen 2.5 Math 7b and LLaMA 3.2 to 3b Instruct, and 1200 for DeepSeek R1 Distill Qwen 1.5b, unless we observe a significant drop in performance. We save the model in safe tensor format for easier evaluation, similar to the approach used in DeepScale R. For evaluation, we employ the official Qwen 2.5 Math evaluation pipeline, using 6 established mathematical reasoning benchmarks: MATH 500, AMY 2024, AMC 2023, Minerva Math, Olympiad Bench, and AMY 2025. We also include non-mathematical reasoning tasks, Arc Easy and Arc Challenge. The maximum number of generated tokens is set to 3072. For Qwen-based models, we use the Qwen 25 MathCot prompt template, while for Llama and distilled models, we stick to their original chat templates. We set the evaluation seed to 0 and the top probability to 1. For MATH 500, we set the temperature to 0. For AMY 2024, AMY 2025, and AMC 2023, which have only 30 or 40 questions, we repeat the test set 8 times for stability and evaluate with a temperature of 0.6, reporting the average pass at 1 performance. We use 4A100 GPS for evaluation. The evaluation settings for LLaMA 3.2 to 3b Instruct and DeepSeek R1 Distill Qwen 1.5b are similar, with each using its own chat template and a maximum token generation of 8192 for DeepSeek. We typically report the performance of the checkpoint that achieves the best average across the 6 benchmarks. However, in specific sections, we report the best performance for Math 500 and AMY 2024 separately, as they may differ. We note that slight performance variations due to numerical precision do not affect our conclusions. In our observations of one or few shot RLVR, we find that using just 1 or 2 examples can yield results comparable to those obtained with datasets containing thousands of examples. Our analysis shows that one-shot RLVR with math examples enhances generalization on non-mathematical reasoning tasks. To explore this further, we analyze one-shot RLVR in detail. We also examine the examples that yield strong results. We list instances of 2 specific problems, which we refer to as Pi 1 and Pi 13. For Pi 1, we see it is a straightforward algebra problem with a physics context. The key steps involve determining a specific value for a formula and calculating the cube root of a number. Notably, we observe that the answer is not exact. A more precise answer would be around 12.7 instead of 12.8. Interestingly, the base model nearly solves Pi 1 without any training, showing high probability in solving key steps. However, for the final calculation, the model produces varied outputs, with a significant portion being close to 12.7. For Pi 13, which is a geometry problem, the base model also achieves a precise answer in a notable percentage of outputs. Further details on other examples used in our study can be found in the appendix. Section Summary. In this section, we outline our training methodology, including default settings for loss coefficients, batch sizes, learning rates, and model checkpoints, while also detailing our evaluation process using various mathematical reasoning benchmarks. We observe that our one-few-shot RLVR approach achieves comparable performance to larger datasets, indicating strong generalization capabilities, and we analyze specific examples that illustrate the model's problem-solving strengths and weaknesses. Section: Post-saturation generalization. Continual generalization beyond training accuracy saturation. In this section, we discuss an intriguing phenomenon we observed during the one-shot RLVR process. As illustrated in our figures, since we only use one training example, we expect the training accuracy for our models, denoted as pi_1 and pi_13, to quickly reach around 100% before the 100th step and stay there throughout training. However, we notice that the performance on the test set continues to improve. For pi_1, we see an average improvement of 3.4% from step 100 to step 1540, and for pi_13, there is a significant 9.9% average improvement from step 500 to step 2000. We refer to this occurrence as post-saturation generalization. Interestingly, we do not see this phenomenon with multi-example datasets like DSR sub, where test performance starts to decline before training accuracy stabilizes. Additionally, when we compare training and evaluation responses, we find that at the end of the one-shot RLVR process, the model tends to overfit the single training example by incorporating the correct calculation process into lengthy, confusing multilingual outputs. Despite this overfitting, the test responses remain accurate, indicating that post-saturation generalization persists even after the model has overfitted. Notably, the overfitting occurs quite late, with pi_1 overfitting after 1400 steps and pi_13 after 1800 steps. Given that each example is sampled 1024 times per step, this means the model overfits the single training example after millions of rollouts. We provide further analysis of post-saturation generalization in another section. Next, we explore whether one-shot RLVR is effective across various examples and domains. Since we provide only one or a few examples for training, we question whether a problem from one domain, like algebra, primarily helps the model with similar questions or if it aids in solving questions from all domains, such as geometry or calculus. We also investigate if different data types behave differently in one-shot RL. To address these questions, we select data with high, medium, and low trajectory variance from various topics and categorize the questions based on their characteristics. Our findings, detailed in our tables and figures, reveal that one-shot RLVR enhances performance across all domains in Math 500, not just the domain of the single training example. Furthermore, while different examples yield varying performance levels, they all provide around or more than 30% improvement, except for those that fail to reward the model. This suggests that nearly all examples are suitable for one-shot RLVR. Additionally, the differences in test performance among examples can inform future data selection methods. We also note that combining examples haphazardly can sometimes lead to smaller improvements, as seen when the subset containing pi_1 and pi_13 performs worse than using either example alone. Lastly, we find it counterintuitive that test data from the same category as the single training example does not always lead to better improvements. For instance, pi_11, which belongs to the number theory domain, scores lower with RLVR compared to other examples from different domains. Similar observations apply to other examples as well. This suggests that the reasoning capabilities stimulated by an instance cannot be easily predicted based on superficial features like domain categories. Section Summary. In this section, we observe a phenomenon called post-saturation generalization, where the model continues to improve test performance despite achieving 100% training accuracy with a single example, indicating that overfitting occurs late in the training process. Additionally, we find that one-shot RLVR enhances performance across various domains, not just the one represented by the training example, and that the effectiveness of different examples can vary significantly, challenging assumptions about the relationship between example categories and performance improvements. Section. More frequent self-reflection on test data. In this section, we present another observation regarding one-shot RLVR. It enhances the frequency of self-reflection in model responses as training advances. To explore this, we analyze the output patterns from various checkpoints during the training of one-shot RLVR on the Quen 2.5 Math 1.5b model. We notice that self-reflection often includes terms like rethink, recheck, and recalculate. Consequently, we count how many responses include these terms while evaluating 6 mathematical reasoning tasks we mentioned earlier. The results are illustrated in a figure. Initially, we observe that after about 1,300 training steps, the length of responses increases significantly, along with a rise in entropy loss. This aligns with our earlier observations, suggesting attempts at diverse outputs or potential overfitting. Additionally, we find that the base model already shows some self-reflection processes, supporting findings from recent studies. As training progresses, the frequency of self-recheck processes increases, indicating that the model generalizes well on test data and demonstrates more complex reasoning, even if it risks overfitting the training data. Interestingly, for the 1,200-step deep-scale R subset, we see a slight decrease in reflection frequency as training continues, which corresponds with a reduction in response length. Next, we investigate whether one-shot or few-shot RLVR is applicable to other models and reinforcement learning algorithms. We examine larger models like Qwen 2.5 Math 7b, different model families such as LLAMA 3.2 to 3b Instruct, and the distillation model DeepSeek R1 Distill Qwen 1.5b. We also apply one-shot RLVR with the PPO algorithm. The results are summarized in a table, with detailed outcomes provided in the appendix. We find that for Qwen 2.5 Math 7b, one-shot RLVR improves performance by an average of 17.8% across 6 benchmarks, while 4-shot RLVR performs comparably to RLVR with a 1,200-step DSR subset. Additionally, we discover that a selection based on historical variance scores yields better results than random sampling. For LLAMA 3.2 to 3b Instruct, the absolute improvement from RLVR is smaller, but few-shot RLVR still matches or exceeds full-set RLVR performance. We also note the instability of the RLVR process for this model in the appendix. For Qwen 2.5 Math 1.5b using PPO, RLVR shows a 16.2% average improvement. In the case of DeepSeek R1 Distill Qwen 1.5b, the performance gap between few-shot and full dataset RLVR is more pronounced, yet both one-shot and 4-shot RLVR yield average improvements of 6.9% and 9.4%, respectively. We observe that model performance for one-shot RLVR declines after about 100 steps, while 4-shot and 16-shot RLVR continue to improve. We hypothesize that the distilled model may need more examples to stabilize the RL process, which we plan to explore in future work. In our analysis, we focus on understanding the mechanisms that enable RLVR to function effectively with just one or a few examples. We hope these insights will inform future research. In our discussion about the reasoning capabilities of base models, we find that the success of one-shot and few-shot RLVR supports the idea that base models possess strong reasoning abilities. For instance, Dr. GRPO has shown that base models can achieve significantly better performance without templates. Recent studies further confirm that as the number of examples increases, models trained via RLVR tend to perform worse than the base model. Our findings reinforce this perspective, as a single example adds minimal new knowledge. Moreover, our experiments indicate that using very few examples with RLVR is sufficient for significant improvements in mathematical reasoning tasks. Therefore, it is essential to explore how to select the right data to effectively engage the model during the RL stage while ensuring data efficiency. Section Summary. In this section, we observe that one-shot RLVR enhances the frequency of self-reflection in model responses as training progresses, indicated by an increase in terms like rethink and recheck. Additionally, we find that one-shot RLVR is effective across various models and algorithms, consistently improving performance on mathematical reasoning tasks, while also highlighting the strong inherent reasoning capabilities of base models. Section: Ablation Study. Policy gradient loss is the main contributor, and entropy loss further improve post-saturation generalization. In this section, we explore the impact of different loss components on the performance of our model, particularly focusing on the policy gradient loss and its role in post-saturation generalization. We observe that in one-shot RLVR, the model achieves high training accuracy on a single example while still performing well on downstream tasks, a behavior reminiscent of grokking. This raises the question of whether our performance improvements are linked to this phenomenon. To investigate, we conduct an ablation study by systematically removing or altering components of the loss function. Our findings indicate that when we eliminate all loss components, the model's performance reverts to that of the initial checkpoint. However, even with just the policy gradient loss, we see significant improvements in performance on tasks like Math 500 and AIME 24. Adding weight decay and KL divergence does not notably enhance performance, but incorporating entropy loss leads to further gains. We note that while entropy loss is beneficial, using a coefficient that is too high can destabilize training. Our results suggest that the success of one-shot RLVR primarily stems from the policy gradient loss, distinguishing it from the grokking effect, which is heavily influenced by weight decay. We confirm that using only policy gradient and entropy loss yields results comparable to the full loss function. Additionally, we find that promoting diversity in model outputs, such as through entropy loss or adjusting the softmax temperature, can enhance generalization. Our experiments show that without entropy loss, the model's performance plateaus after a certain point, but reintroducing entropy loss and adjusting the temperature leads to further improvements. We also examine cases where the model struggles with difficult examples, yet still outperforms the base model. This challenges our earlier assertion that policy loss is the sole contributor to performance gains. By removing policy loss, we still observe significant improvements, indicating that entropy loss can independently enhance performance, albeit to a lesser extent. Finally, we experiment with different label scenarios, revealing that slight inaccuracies in labels do not severely hinder performance. However, if a label is incorrect yet guessable, it can lead to worse outcomes than using an unguessable label. These insights may inform future research on label robustness in RLVR, and we plan to further investigate the role of entropy loss in our future work. Section Summary. In this section, we demonstrate that the performance gains in one-shot RLVR primarily stem from the policy gradient loss, while the entropy loss further enhances generalization post-saturation, albeit with careful tuning to avoid instability. Our findings also indicate that entropy loss can independently contribute to performance improvements, suggesting its potential role in label robustness and generalization in future research. Section: Related Work. In this section, we discuss related work on reinforcement learning with verifiable reward, RLVR. RLVR uses a rule-based verification function to calculate rewards, which has proven effective in enhancing the reasoning abilities of large language models, LLMs. Typically, in RLVR applied to mathematical reasoning datasets, we match answers. The reward function gives a simple yes or no based on whether the model's answer aligns with the correct answer. This straightforward reward design eliminates the need for more complex reward models, making it both simple and effective. The success of RLVR is bolstered by improvements in reinforcement learning algorithms, such as optimizing value functions and refining techniques in proximal policy optimization, PPO, including various enhancements like Vine PPO and VC-PPO. Additionally, we see advancements in stabilizing and speeding up generalized policy optimization, GRPO, methods. We also note that data selection for post-training of LLMs has been widely researched, mainly focusing on supervised fine-tuning. These methods include assessing quality using LLMs, utilizing features from model computations, and gradient-based selection. Another area of research looks at data selection for human preference data in reinforcement learning from human feedback, RLHF. However, data selection specifically for RLVR is still underexplored. One example is LIMR, which selects 1,400 examples from a total of 8,500 for RLVR to achieve comparable performance. However, unlike our approach, they do not test the limits of using a very small training set, such as just one example. Another related study indicates that using PPO with only 4 examples can lead to significant improvements, but they do not systematically investigate this finding or prove that such a minimal training set can perform as well as using the entire dataset.